Hello guys, and welcome in this new recording. Today we're going to continue the list of tutorials that we started last time. We have been through the reduction algorithm that you can implement on web GPU, and now we're going to continue with the prefix-sum algorithm implementation, again using WGSL, so for web GPU. Okay, let's get started. The first thing I would like to mention here is why exactly would you want to go this way? I mean, in my case, why am I going in this direction? And the answer is I'm actually still working on the procedural tree generation system and the tree designer tool. I made a couple of recording on this one already, and it's not completed, but this got me thinking, and I was already wondering how could I handle, well, a lot of trees, like million of trees, and how could you still render that somewhat efficiently. And this basically led me to reading a lot of additional papers, and there are a few of them concerning how you would do the calling process on the GPU. And in fact, I started to implement this on my own, and I realized that in the implementation that I have been building, at least, I will eventually need some kind of partial prefix-sum computation. What I mean with partial implementation is that what I need on my side is really just a prefix-sum on a workgroup shared buffer. So I don't need to do a prefix-sum computation on a complete buffer, but just a bare workgroup. So as I said, so you could have a large buffer, and you are going to cut that into smaller pieces, and then you may have some input elements, and you're going to handle that in a single work group. Then this will be another one, and so on. And all I need to do is that each work group would need to filter all those input elements and just figure out, okay, at the end only 4 or 5 elements should survive, and the next work group would do the same kind of thing, but they both don't need to accumulate the result in a single device memory buffer. Okay, so that's the idea, and the way it would work is that I'm going to provide all the 3 locations to compute shader, and this compute shader is going to use each of those 3 locations in addition with a bounding box for the tree itself, to figure out if you are actually in the view frustum or not, or at least if the bounding box is intersecting the view frustum. So this way you can figure out that a few of those locations are going to be valid, so you need to render the trees at those locations, and all the other locations that are outside of this view are going to be discarded. So, well, how does it work? From there, you can just imagine that you are going to process the large location list buffer per chunk. So you cut that into a chunk, and each work group is going to process those 256 locations separately. And so yeah, then for each location you're going to figure out, okay, this is still in the view frustum, this one is not, it's not, this one is not, yes, and so on. So you can figure out what are the surviving locations. And when you have this, you can then put a flag for those locations. So you could say 1 for a valid location and 0 otherwise. So if you think about it for a moment, then that's all you need to compute a prefix-sum. and you can just start counting with this one. Then you had 0, so it's still 1. Then you had again 0, you stay at 1. Then you had 1 again, so you reach 2 this time. Then you're still at 2, and so on. So you see that you are going to count the values and you're going to increase that progressively, but sometimes you may just not increase anything and stay to the current value. Once you have computed this, I mean, this is where you actually do the prefix-sum. And once you have computed that, you're going to use only the threads that have a surviving location if you want. So all the threads where you have those green points, and those threads are going to read from the computed prefix-sum what is the appropriate index where you should store the corresponding location. And that's how you can then compact those green points here like that. And so yeah, once you have that for a given work group, well, it's just a part of the algorithm, because then you have another part which is then going to accumulate this into a device memory buffer, but we're not going to go into those details for the moment. Next point I need to mention is what are the references are actually used for this prefix-sum experimentation. First thing I started with is this WebGPU GitHub repository, because there's a page, let's see that, where they are discussing the possibility to introduce support for subgroups in the WGSL language. And fortunately, it's still not really available for the moment. I guess this is coming after the version 1.0 is out. So yeah, not ready yet. And this is where you can find, in fact, a first version of how you could compute prefix-sum. Very simple version, which is not using this subgroup concept, and so it's not that efficient. But this is actually the first version I seen myself. After that, the next most significant input which I use is this repository from Bone164. It's actually not Bone but B0. And the thing is, if you go on this repository, the latest version that you get is this page, but it's actually giving you an indication that the survey is currently not available because it's being updated. So if you want to see what I actually use myself, you need to go to the comments here, and for instance, if you go with this one, before you got those latest update, so add split dispatching for very large dispatches, okay, then you just go into browse files and you get the previous version of the readme file, and that's where you have actually a pretty nice list of all the algorithm that you might want to use for prefix-sum computation, at least in DirectX 12 and also in CUDA, and I think there's also part of it in the Unity, but it's not maintained anymore. So I use that as a reference to figure out, well, what I could try to implement in the WebGPU, and we'll get back to this. And finally, the last resource that I have used is this one, so GPU Gems 3 chapter 39. So this is a page, and again here it's providing you a pretty nice explanation of how you could do this prefix-sum implementation, starting with a naive version and then improving on this with a couple of steps. So I didn't really implement the naive version at all, and I started with the work efficient parallel scan version, which in fact is basically doing a reduction as a first step. So this is what we've done before. But then it's going further, and there are more steps in the algorithm to compute this prefix-sum array properly. And there's also another consideration where you actually need to change the code to avoid bank conflicts. So that's the latest version which is provided with the changes mentioned here. Okay. So that's it for an overview of the references that was used in this experiment. Before we go into the unit test overview, one thing I need to mention is this. The best thing that you can do, in fact, I mean, that's what I've found so far for this prefix-sum computation is this algorithm. So I have the image here in big. So the chain scan with decoupled look back. Unfortunately, this is not available yet in WebGPU because you would need the support for those subgroups, functions and everything. And so I'm not very familiar with the details, but the idea is really that when you're executing a warp, you have some function that you can use, in fact, to get the threads to communicate between them in the warp itself without relying on the shared memory arrays. So that's even faster than sending the data into the shared memory. So that's how you can achieve the best performances, like in this case. But for us, it's not really an option. So yeah, we have to wait a bit more, I guess. But anyway, what I did then was to mainly use the implementation that are described here as basic scans. So you don't have that many of them, because afterwards you're going to move to the warp synchronized scans. And I think starting from here you need some consideration of when you see things like that, wave, prefix-sum, wave, read lane first. I'm pretty sure these are not available in WebGPU for the moment, so I didn't insist that much on that part. Anyway, let's have a look at the unit test itself now and the different version that we have available. So this is a unit test, and it's built in a similar way to the reduction unit test. So we have this run prefix-sum function, and after that, so it's a pretty big function actually. After that we have the actual unit test, and we're going to run a few of those tests using this prefix-sum. And currently I think I have disabled this, but I can just re-enable this for the moment. Alright, so what do we do in there? We're going to call this function for every setup that we have. It's going to prepare an input array as usual, then going to retrieve an output array. What is different compared to the reduction algorithm is that now the output array is really an array, and it's supposed to be as big as the input because you want all the values ordered. Whereas for the reduction, you just wanted to compute the sum of all the values, so you just needed a single integer output. Okay, we've seen this reduction factor mechanism. We discussed that in the previous recording, and then it's basically doing the same thing. Going to execute this compute pass with a single compute step in there, and execute that a few times and monitor the time it took for every single execution. And then when it comes to comparing the output, then you have the output that you're going to read from this buffer, and you have the expected values. So expected values, as I said, we're going to just perform the prefix-sum per row group. It means that we have some input in the array, so we're first going to cut this array into the appropriate size for a single work group, and then we're going to order the values in this chunk of the big input buffer, and we do that for every single chunk. So it's not a completely ordered buffer that you get at the end. But never mind, as I said, I don't really need to push it further for the moment, so that's okay with me. Alright, and then concerning the different versions that we have available, I started with this one, prefix-sum 0, which is coming directly from the NVIDIA paper, which I mentioned here, so chapter 39. And I was really using the latest version, the one with the conflict-free access to the shared memory. So we have this version of the shader here. Okay, I'm not going to go into all the details, so maybe just giving you a quick overview. We're going to do this in different parts. So you have this part here, which is the upsweep thing, I think. And then you are clearing the last element. So this is mentioned in the paper. If you check the small diagrams here, so the upsweep, that's it. This is the upsweep part. This is a reduction computation, in fact. Then there's a step where you need to put the last value here to 0. And then you have this downsweep where you're going to propagate your data downwards. And so this is the last part, which is here. And that's it. Then you're going to write the output in the output buffer. In fact, I think, yeah, when I was reading this, it's a bit tricky to figure out exactly what is the shader, the complete shader. So I have actually rewritten those shaders, those CUDA shader on my side, in a way that is more easy to read. So that's naive implementation, that's optimized version, and this is the final version with bank-free access to the memory. So the structure you see is the same as what we have in the WGSL, because in fact I use this code here as a reference code. Alright, now concerning the performances, I think this was pretty good, but not really fantastic at the same time. If, for instance, we try to run this prefix-sum 0 on its own, we get 230 gigabyte per second. So this one is 230 gigabyte per second. Next, I kept testing further, starting with this Alice Steel version, which is the one that you have available in the GitHub issue here. So this simple code here. So this is the implementation that I got on my side. It should basically be the same thing. I'm just providing what I need as input here to perform the computation. And again, if we give it a try on its own, yeah, I remember I was a bit surprised with this result, but it seems that this is running faster than the NVIDIA implementation. So you just put a very doomy simple code like that, and it's working better than the efficient version. So a bit surprising, but I don't know, maybe also again, when I'm not sure, maybe the timing that I'm computing is not good somehow, but otherwise it means that this version is really better. For this one, we have about 260 gigabyte per second. Next, I continued on this path with additional algorithms, so the Slanky and the Brent Kung, and also reduce and scan version. Those three implementation are coming from this Bone repository. So you have the Slanky version here. Where is it? Oh, interesting, it's not displaying anymore. Maybe I should have kept a proper copy of this repository before all those changes were introduced. Maybe I should go deeper then. Nope, doesn't seem to work anymore. That's a pain. But never mind, let's just have a look at what we have in the code itself. So after the Ilias Steel version, I actually tried a custom implementation, but that was not really working properly. Then, as I said, I tried the Slansky version. So that was the prefixsum version 3 initially, and also the Brent Kung version 4 and the prefixsum 5 reduced and scan. And the performances again were all approximately similar, so 200 and something gigabyte per second. Then I started to experiment further on a different version and small changes, for instance on the ill steel. So you see here I have the first reference implementation, and then I had this version B here, which is different. I don't remember exactly what I was trying here, but in the end it was not really improving anything, I think. In this one, for instance, I tried to provide multiple inputs at the same time. So same idea as what we were doing with the reduction shader. If you provide multiple elements in a single thread and you process them, for instance, here in a vec4, that's going in theory to help in some cases to improve the performances. I think this was helping a little bit, but the results were not that amazing. Then this one, not sure what it is doing exactly. And here I was pushing this further and using 2 vec4 to use 8 inputs at the same time. Where I actually really got better result is on this one, the Slansky implementation. And in this case here, I have been optimizing the reference version more aggressively, and for instance I was unrolling the loop that was suggested in the reference code. And if you do that, you realize that you may also not need the workgroup barrier at every single step of the for loop, so you can reduce the number of workgroup barrier here. And you also don't have to write all your result into the shared memory at the end, so you can just do some computation on the fly. And I was also providing 4 input value for each thread here to store them in a vec4, as you can see here. And this was in fact providing pretty good result. So if I try, for instance, to run the Slansky 3B and 3C versions, then you can see that the results are pretty high. So 350 gigabyte and 360 gigabyte, which is in fact the best result that I could achieve so far. It of course doesn't mean that this is a best algorithm, because you could probably perform some of the optimization that I've done here on the other implementation, like Ilias on Brenker, I don't know. But it was pretty satisfying already to get to this far. So as noted here, the best output that I could get so far is in this range. But what we need to keep in mind here is that I'm really doing the computation for a workgroup level prefixsum computation only, so not a global prefixsum computation. And finally, let's have a look at some comparison now, because this is also interesting. If you refer to this image from the Bones repository, you see that the best output that you can get is here, 5.42 multiplied by 10 to the power 10. And that's a number of 32-bit elements per second. So if you use that, you can compute that it's corresponding to about 200 gigabyte per second. And now if you take that bandwidth, the maximum bandwidth that you have for this GPU, because apparently this is a GPU that was used here for the computation of those data. So if you use this value, you can figure out that the efficiency of the usage of the GPU basically is about 40%. And now if we do the same thing on my side here, I was using this GPU, so that's the maximum bandwidth, and this is the bandwidth that I can achieve. You get an efficiency of about 37.4%, which is pretty surprising. But you have to keep in mind, yeah, that we're really doing the computation for the workgroup level, so it's not supposed to be as good as the result that we have here. But still, I was very surprised with that because I didn't expect to go with an efficiency that is that high. At the same time, I'm not really sure it makes sense to do this computation because prefix-sum itself is not really about just bandwidth, I guess. You have some computation going on, so maybe it also depends on the GPU architecture and also, yeah, not sure if this means anything. And anyway, I guess this is covering everything I could mention concerning this algorithm implementation. As usual, if you have any question, just let me know in the comments. And otherwise, I'll see you next time. Bye bye.